ஒரு நிமிஷம் வெயிட் பண்ணுங்க.
Visible, very clear, Dr. Divakar.
Yes, sir. Yes, sir. Okay, sir. Shall we start? Yes, sir. Okay. Am I audible to all?
Yeah,
Is it okay? Yes, sir. Yes, sir. Okay. Thank you. Thank you. Thank you, Mr. Pradeep, sir, for your wonderful welcome session. Thank you. So today, this afternoon session, I'm going to talk about engineering thermodynamics, laws and its properties. Since we are a faculty members, we know everything about this. But if it is a faculty development program, I just want to tell about different types of law in engineering thermodynamics with some basic examples. And what are all the properties we need to consider to solve the important equations and the theoretical concepts in engineering thermodynamics. Right. So thermodynamics is available in physics and chemistry. The application of this thermodynamics is available in physics and chemistry. But what is the practical applications is available in the engineering field? That is known as engineering thermodynamics. Thermodynamics, thermo in the sense of heat, dynamics is motion. So how much amount of heat is transferred from one space to another space, one region to another region, so one point to another point. In the engineering field, that will be studying in this subject, engineering thermodynamics. So it is a science that describes how the thermal energy is converted from one form to another form. Okay, so it's a full and full study about heat. Right. So here I have given the three images. See this image. So I'm giving a heat supply to a rod. So there is a candle which give a heat supply to the rod from one end to another end. So we are know that heat will be traveled from one end to another end. Second diagram is that melting of ice cubes. So as soon as the temperature increase in ice cubes, it started to get evaporate or gases. So step by step, it will be attaining the different spaces, different phases like solid phase, liquid phase, gaseous phase. If I give maximum heat, around 75 to 80 degrees Celsius or 10 kilojoule of heat to that particular ice cubes, it will be directly attaining the vapor conditions. So that is known as a sublimation process. So like how the heat is transferred from one end to another end, how the energy is converted from one form to another form. These are all the things we'll be studying in the subject of engineering thermodynamics. So third diagram is a coffee cup, how the heat is transferred from the coffee cup to atmosphere. So this is the just basic example for the engineering thermodynamics. If we teach like this to the students, now they will get more attracted to study this subject. They won't confuse with any mathematical relations, equations. First, if we give a good impact about this subject to the student mentality, student knowledge, then slowly we will solve the equations. Then their attraction, their interest about this subject will be improved. Then we all know this energy conversion techniques. The energy will be converted from one form to another form. So I am using coal to give the heat energy to the boiler. So water is available in the boiler. So water is getting evaporated, steam is generated. That steam is sent to the turbine. So the generation of steam is known as a heat energy. We all know this. So turbine blades will be rotating by using this steam. Turbine blades will be turning. Okay, so the mechanical energy is absorbed in the turbine. That mechanical energy is forwarded to the generator or motor where the electrical energy is generated. After that, we can use it for our practical applications. Again, the energy will be repeated here. The heat energy is converted into a mechanical energy, and the mechanical energy is converted into a electrical energy. I am giving this electrical energy for fan. Okay, we all have fan in our homes, no? So I am giving a electrical energy to the fan. Fan blades are rotating. That is known as a flow energy. Sorry, that is a kinetic energy. So when the energy is then from fan, I'm giving some energy to something. So how energy is transferred from one form to another form. These are all also studying about the engineering thermodynamics. So before to know about the thermodynamics, we should know what is the important parameter to be considered for solving the equations. So temperatures, energy available within the system, and entropy, heat. So this is 4 important terms should be known before solving the equations in engineering thermodynamics. There are 2 types of thermodynamics, classical and statistical. Classical thermodynamics will be studying about the bulk properties. Statistical thermodynamics will be studying about the atoms which is available in that bulk models. Okay, so this is the difference between classical and statistical thermodynamics. Right. So thermodynamics laws and properties I will be discussing in this session. So before to know about the thermodynamics law, before to start the thermodynamics law, we should know what is the zeroth law of zeroth law of thermodynamics. Zeroth law of thermodynamics is invented in the year of 1920. 1920. Actually, the interesting thing is that before inventing zeroth law of thermodynamics, they have found first law, second law, third law. Already they have found what is first law, what is second law of thermodynamics, and they have found about the entropy concepts, and they have found the third law. So they just wanted to know about the thermal equilibrium. So to study about the first law of thermodynamics in an in-depth manner, they just wanted to know about what is equilibrium and thermal equilibrium. So they have invented one law. They have confused that what name we have to suit for this law. So finally, they have named this law as a zeroth law of thermodynamics. So zeroth law has been found after the invention of first law, second law, third law of thermodynamics. So before to know about the zeroth law of thermodynamics, we should know what is equilibrium. Equilibrium in the sense equal. Equilibrium means equal. So I'm having a system. Properties which is available inside the system should be equal in all the directions, in all the spaces, in all the regions. That is called equilibrium. Thermal equilibrium in the sense the energy, heat energy, the temperature which is available in that particular room or system is equal in all the space, all the regions. The molecular temperatures, the atom temperature which is available in that particular system is equal. That is known as a thermal equilibrium. So what they are telling to say in a zeroth law of thermodynamics is that A and B body is in contact with each other, having certain thermal equilibrium. That two bodies are connecting the C body means C body also will be in thermal equilibrium. So A equal to B, B equal to C, C equal to A. So A and B is in thermal equilibrium with each other. That A and B is connecting with the C body means C body also will be in thermal equilibrium. So if a person has a fever, his body temperature will be transferred to another person. Okay, so that is called thermal equilibrium. So heat is transferred from one body to another body, then attaining the same temperature. See, this is the basic example to understand about the zeroth law of thermodynamics in an easy manner. So I'm having a room temperature is 30 degrees Celsius. In that room, I'm having a coffee cup. The temperature of a coffee cup is 50 degrees Celsius. I'm having another coffee cup which has a temperature of 10 degrees Celsius, So after 30 minutes later, the room temperature is the same, 30 degrees Celsius. That 50 degrees Celsius coffee cup is losing its heat to 30 degrees Celsius. And that 10 degrees Celsius coffee cup is gaining the heat from the atmosphere and having a temperature of around 30 degrees Celsius. So these three will be attaining the thermal equilibrium. Is it possible? Practically, yes, it is possible. Your room temperature is 30. If you are keeping a coffee cup at 45 or 60 degrees Celsius, after 10 minutes or 1 hour later, that coffee is attaining the room temperature. The coffee temperature will be equal to the room temperature. If you keep 15 degree or 10 degrees Celsius of coffee in your room, after 10 minutes or 30 minutes later, that 10 degrees Celsius coffee will be attaining the room temperature. Is it possible? So this is the basic example for zeroth law of thermodynamics. Two bodies are in thermal equilibrium with a third body. That third body also will be in thermal equilibrium. Right. Then first law of thermodynamics. So we all know that energy we cannot create. We cannot demolish this energy also. So it will be transferred from one form to another form. So I have given the example. I have told about this coal is converting as a heat energy. Then that heat energy is travel to turbine, the mechanical energy is generated, then that mechanical energy is converted into a useful electrical energy by the help of a generator or motor. So energy is neither be created nor destroyed, can be transferred from one form to another form. This is first law of thermodynamics, right? So don't confuse about the equations. We are all first, if we see any equations, we will get confused. Oh, we will lose our interest to study that particular subject. If we understand the concept, science behind that laws or any statement, then it will be very easy to know that equations. So first we should try to understand the basics and the science behind that particular definitions or laws. So let us take a system. I'm giving a Q input to that system and getting a work output as a work output from that system. So the energy which is already available in the system will be changed. Am I right or not? So before giving Q, that system would have some amount of energy. After the work done, the system energy would have changed somehow. So the change in internal energy is known as is termed as a del E, equal to Q minus W. That's what I just wanted to discuss by using this slide. Conservation of energy. Simply, we are stating first law of thermodynamics is conservation of energy. So how much amount of energy I'm giving as a heat input, that energy I can be getting as a work output, 100% efficiency. But practically, it is not possible. But first law of thermodynamics states that amount of energy input will be equal to amount of work output. Heat input will be equal to amount of work output, right? So here there is a boy having a Q amount of energy. So his internal energy has been changed as a E1. Then he has done some work and his energy is converted as a E2. So what is the work he has been done? We can found by using this formula E2 minus E1 equal to Q minus W. So this is the better example for first law of thermodynamics, right? So after knowing about the first law of thermodynamics, we should know some process terminology. Adiabatic process, isothermal process, isobaric, isochoric process. Adiabatic process, there is no heat transfer takes place. What is isentropic process then? The process is happened from one end to another end, that is adiabatic process. If the process is repeated from A to B, sorry, B to A, that is known as isentropic process. When the reversible adiabatic process is known as a isentropic process. Both adiabatic and isentropic process has no heat transfer. Isothermal process, we all know the constant temperature, isobaric constant pressure, isochoric is a constant volume process, right? So in adiabatic process, heat transfer is 0. So obviously Q equal to 0. So we should know what is Q, capital Q. Capital Q will be denoting about the heat transfer of particular system or medium, that is Q. We have seen some term, we have seen a term as a small q. What does that mean? Small q will be defining about heat flux. What is called the heat flux? Heat flux in the sense the amount of heat transfer in per unit area. Per unit area, how much amount of heat is transferred? So that will be denoted as a small q. Capital Q will be denoted as the heat transfer in an entire area. So for the adiabatic process, Q will be 0. If a Q is 0, del U equal to W. If the work is done by the system, W will be the positive. If the work is done on the system, W will be the negative. So accordingly, if W positive, del U will be the negative. If W negative, del U will be the positive. This for the calculation purpose. Then isothermal process, a constant temperature process. Can we maintain a temperature in a constant temperature for the entire day for certain period of time? No, we cannot maintain the system in a constant temperature, but we can assume that if a system is if the system is losing energy in very slow manner, that is known as a constant temperature system. Okay, any heat flow into or out of the system must be very slow enough. Heat is flowing inside or heat is coming outside should be in very slow. If it is happened, that system is known as a constant temperature system. So we can think that that system is attaining thermal equilibrium. That system is maintaining the thermal equilibrium. So for the ideal gases, we all know that temperature difference T2 minus T1 will be the 0. So obviously change in internal energy will be the 0. So if we apply this equation into a first law of thermodynamics, the equation will be changed as a Q equal to W. Right. Then isobaric process. So isobaric process can be explained by boiling of the water. We all know this process already. So we have to integrate the equations. First law of thermodynamic equations. Finally, we will get a W equal to PdV. So by using this equations, we can solve the problems in a first law of thermodynamics. Isochoric process. Isochoric process is a constant volume process. If a volume of the system is constant, there is no work done takes place. Am I right or not? If any work is happens, the volume will be changed. If no work is happens, the volume will be maintained constant. So W will be the 0. Finally, the thermodynamic first law equations will be become as del U equal to Q. So heating gas in a closed container is known as a isochoric process. Heat capacity. So many of the student doesn't know about this definition of heat capacity. So heat capacity is nothing but I need to increase the temperature of materials to 1 degree Celsius. Let us take any phone or any charger or any red pen or blue pen. I'm having a pen. That pen temperature is 25 degrees Celsius. Let us consider that pen temperature is 25 degrees Celsius. I just want to increase that pen temperature 25 to 20 degrees Celsius at 1 degree Celsius. I just want to increase the pen temperature to 1 degree Celsius. For that, how much amount of heat I have to give? For that 1 degree Celsius improvement, how much amount of heat I have to give as a input? That is known as a heat capacity. Okay, so the general formula for the heat capacity Q equal to mCp delta T. For all the components, for all the materials, heat transfer rate will be found by using this equation only. Q equal to mCp or mCv delta T according to the constant temperature process or the constant pressure. The unit of Cp is joule per kilogram Kelvin. So these are all the general values for calculation purpose I have given. Cp, Cv values. R is a universal gas constant. Cv 0.718 kilojoule per kilogram Kelvin. I am given a unit in a kilojoule per kilogram Kelvin. Cp 1.005 kilojoule per kilogram Kelvin. Gas constant 0.295. Next, second law of thermodynamics. So there are two statements about the second law of thermodynamics. One is Clausius statement, another one is a Kelvin-Planck statement. Clausius is telling that heat will be transferred from hot body to cold body. So heat will not transfer from cold body to hot body. It is not transfer from cold to hot, but hot to cold heat will be transferred. Whether it is possible? Yes, we can identify that heat will be transferred from hot body to cold body, but it is not at all repeated. Cold to hot, it is not at all happening. Okay. So second law of thermodynamics is giving the direction of heat. So in the first law of thermodynamics, we can identify that heat is converted into one form. It is converted into one form to another form. But how, in which direction it is converted? That we can identify by using this second law of thermodynamics. So let us have a coffee cup. Whether a coffee cup losing its heat to the atmosphere or it will be absorbing the heat from the atmosphere. We all know that the coffee cup is losing its heat to the atmosphere. So we can from this we can identify that the direction of the heat. Okay. Next statement is Kelvin-Planck statement. So he is telling that it is impossible to construct a 100% efficiency engine. So he is violating the first law of thermodynamics. First law of thermodynamics states that amount of heat input will be converted into a amount of work output. So 100% efficiency can be achieved, like that conservation of energy principle stating. But Kelvin-Planck saying that it is not impossible to construct a machine which gives 100% efficiency. losses will be there. He's telling that the losses will be there. So he's taking a heat engine. So he's giving 100% heat input to the heat engine, and some of the heat is converted into a useful work, and wasted heat has been sent to the cold reservoir. So waste heat is absorbed in a cold reservoir. So he's also finding that direction of heat. So direction of heat flow. So he's telling that it is impossible to construct 100% efficiency. No engine will give 100% efficiency. That is the second law of thermodynamics. Right. The heat engine, we all know that a device which transforms the heat into the work. So hot reservoir will be supplying the heat, that will be denoted as a QH. Cold reservoir will be taking the excess energy, waste energy, that is known as a QC. So obviously for the calculation purpose, we can take QH will be positive value, QC will be the negative value. So from the second law of thermodynamics, we should know about the cycles. So we know Otto, diesel, Carnot cycles now. So Otto cycle is a petrol, diesel cycle is a diesel engine, is a constant pressure cycle. Otto cycle is a constant volume cycle. Carnot cycle is a ideal imaginary engine. So which has 100% efficiency, right? Entropy. So many of the faculty members are also confusing about this term of entropy while teaching to the students. Obviously, students, I didn't see any students explain about the entropy concepts very well in my teaching experience. Actually, if they got any questions about entropy, simply they will leave in exam papers. If we ask about the questions of entropy, they won't speak. Enthalpy, they will speak about enthalpy, but they won't speak about entropy. They are confusing about what is entropy. Even some of the faculty members are also getting confused about the entropy. Here I will explain what I have observed about the entropy concepts. Entropy is nothing but it's a disorder. So any molecules which is present in a system will be in certain order, will be in certain perfectly arranged manner. If it is collapsed, if it is in a disorder condition, that is known as entropy, randomness of a system. Or sometimes we can state this as a unavailable energy. We can see this entropy with a practical example. So we all know that law of conservation of energy. Energy is a transfer from one form to another form. Here see the first image. Two child is lifting the weight, so they are giving a energy. So their potential energy which is inside the body is converted into a kinetic energy. They are lifting the weight and moving from one place to another place. So energy is transferred from one form to another form. The second slide is second child is using hammer, and his potential energy is converted into the kinetic energy. So he is giving a heat. Third diagram, fish is jumping from one tank to another tank. So fish potential energy is converted into a kinetic energy. The energy which is possessed during the traveling condition, that is a kinetic energy. In the dynamic motion, that is a kinetic energy. So LPG gas cylinder chemical energy is converting as a heat energy. So here there is a battery. So battery is giving a chemical energy. Battery is having a chemical energy. That chemical energy is converted into a electrical energy. So energy is converted from one form to another form. Here we just want to know about the entropy concept by converting this energy process. See, so from LPG gas, I'm giving a heat energy to the bowl. So chemical energy which is available inside the cylinder is converted into the heat energy. So I am heating the water. So that water having a temperature of around 70 degrees Celsius. I am keep it in a room temperature. So as soon as time passes, after 30 minutes or 40 minutes, that 70 degrees Celsius water losing its heat to the atmospheric temperature. So that water temperature will be equal to the atmospheric temperature after half an hour later. Where that energy gone? I have given the energy from the cylinder to bowl. Chemical energy is converted into the heat energy. So from that heat energy, I have attained the temperature of 70 degrees Celsius. After half an hour later, that 70 degrees Celsius again came to its original room temperature, 25 or 27 degrees Celsius. So where is that energy gone? That energy is released to the atmosphere. That energy is released to the atmosphere. That is unavailable energy. That is known as entropy. So entropy is an unavailable energy which cannot convert into a useful work. So I have attained the 70 degrees Celsius of boiled water. So as soon as the time passes, that 70 degrees Celsius is reduced to the room temperature. So where is that energy gone? So what is the work I have done for that particular heating water? That energy has gone somewhere. So that is called unavailable energy. That unavailable energy is known as entropy. Where is that energy gone? See, that energy is mixed in the atmosphere. That energy is mixed in the atmosphere in the sense that energy is mixed in the kitchen. That energy is mixed in the kitchen. So what is the energy already available in that kitchen is getting expanded because energy losses is happened in that kitchen. So already energy which is available in that kitchen is getting expanded. So that energy cannot be converted into a useful work. So the energy which is available in the kitchen is expanded, increased, but that energy we cannot capture and we cannot convert into a useful work. So entropy is a unavailable energy which cannot be converted into a useful work. Can you get me? Again, one time I will explain. So I am giving a chemical energy and converting that chemical energy to the heat energy in a bowl. So I'm having a 75 degrees Celsius of hot water. So I'm keeping it in a room temperature. So after half an hour later, that 75 degrees Celsius is reduced to the room temperature. So where is that energy gone? That energy is mixed in that room. So already available energy in that room is getting expanded and that is mixed in that room. So we cannot capture that energy to convert into a useful work. This is known as a entropy. So when the molecules in that room is getting disorder or randomly flowing from one space to another space, energy will be created, but we cannot capture that energy to convert into a useful work. That is known as a entropy. So see these ice cubes. So from the ice cubes, the molecular which is molecules which is arranged in ice cubes in a perfect manner we can consider. Okay. So I'm giving a heat input to the ice cubes. It is converting as a liquid. After that again I am giving a heat. Then it is converting as a vapor. Okay, so when the molecular changes happens, when the molecules which is available inside the system is moving very fastly, entropy is increased. The forces which is happens inside between the molecules is enhanced means entropy will be increased. See this graph. In a solid to liquid, entropy increased. From liquid to gas also, entropy increased. So whenever I am giving a heat input, the force which is happening between the molecules will be increased. So the traveling of the molecules will be enhanced. So the entropy of the system is improved. So this is how we need to understand the entropy concept. This is very simple thing. Disorder. When the molecules are travel from one position to another position, force is created. If the force and the pressure is happen inside the system, temperature will be slightly improved. The temperature improves automatically. The entropy of the system is improved. Heat energy will be generated automatically. The entropy of the system will be increased. So this is another example for the entropy concept. Big Bang theory. We all know that Big Bang theory. Our universe is created by the process of explosion. Big Chill theory is stating that the energy which is available in this universe is getting expanded day by day. Big Chill theory is stating that the energy which is available inside the universe is expanding day by day. So this is called the increase in entropy. So this is called entropy principle. So entropy of the universe will be increasing day by day. The aging process. The chemical reaction the chemical molecules structure disorder happening in our body. That's why we are getting aging. So this is a proved concept. So there is an article in this entropy aging process also. So aging process also one of the example for the entropy increase in entropy. So our body is a chemical, our body is running in a chemical reaction. So whatever the molecules which is available in our body, so due to the chemical reactions, that molecules will be having a disorder. So randomly it is moving from one position to another position. That's why we are getting aged. So aging process also one of the better example for the entropy concepts. So before to know about the third law of thermodynamics, we should know what is entropy. So we came to know what is entropy. Now third law of thermodynamics. The entropy of a pure crystalline substance will be zero at zero absolute temperature. So there are three boxes are there. In first box, some molecules are there. In second box, very less molecules are there. And third box, the molecules which is present in that box in a rest condition. So that is arranged in a good manner. So if the molecules are slowly moving, temperature which is available in that system will be decreased. Kinetic energy will be decreased. So if it is again that a molecular force is reduced and that a movement is slowly happening means again the temperature will be reduced, kinetic energy also reduced. Third diagram, if it is not at all moving, it is arranged in certain position means obviously kinetic energy will be zero. The temperature is reduced to 0 Kelvin or minus 273.15 degrees Celsius. What they are trying to say is that the entropy of a pure crystalline substance will be zero at zero absolute temperature. Can we achieve 0 Kelvin temperature? We cannot achieve. So we can see that 15 degrees Celsius minus 20 degrees Celsius component, but we cannot make a temperature of a component in minus 273.15 degrees Celsius. That is very difficult. That is not at all possible. So pure crystalline substance also not possible. That type of material is not at all available. So entropy of a pure crystalline substance is zero at zero absolute temperature. What they have seen in the last slide, what we have seen in the last slide, entropy of the system, entropy of the universe is increasing. Practically, we are seeing that. But third law of thermodynamics states that we cannot see a particular material's entropy in a zero conditions. We cannot see that. So that is the third law of thermodynamics. So we cannot achieve 0 Kelvin and we cannot achieve minus 273.15 degrees Celsius also. So this is third law of thermodynamics. So absolute zero temperature in the sense 0 Kelvin. If it is in a degree Celsius means minus 273.15. If it is in a degree Fahrenheit means minus 459.67. Pure crystalline substance in the means the molecular arrangement will be in that materials in a perfectly arranged manner. We cannot see that type of materials. It is not at all possible to make it. So why we are studying the third law of thermodynamics in the sense, we should know that entropy of the universe will be increasing. It is not at all decreasing, and also it is not attaining the value of zero. So that is third law of thermodynamics. So third law of thermodynamics is full and full about entropy concept. So if you study about the entropy concepts, it will be very easy to know about the thermodynamics. So entire thermodynamics chapter will be very easy for us if you know the entropy concepts well. So entropy of the universe is increased. Del S universe will be greater than or equal to zero. So I am taking the equation entropy of the universe equal to entropy of the system plus entropy of the surroundings. I am taking a coffee cup example. So this coffee cup having a temperature of around 45 degrees Celsius. So I'm thinking that this coffee cup is absorbing heat from the atmosphere as a 10 joule. Surrounding temperature is 25 degrees Celsius. So entropy equation change in temperature, sorry, Q divided by T. That is a Classius inequality equation. Na? So I'm giving a value in that equation. So coffee cup is absorbing the heat 10 joule. Q equal to 10 joule. 10 divided by temperature 45 plus I'm changing it to Kelvin 273 plus surrounding. So it is absorbing 10 joule from surroundings means surrounding has lost 10 joule heat. Am I right? So plus 10 divided by 45 plus 273 plus minus 10 divided by surrounding temperature is 25 na? So 25 plus 273. The value del S of universe will be minus 0.00211 joule per Kelvin. Is it possible? We all know that entropy of the universe is increasing. It is not at all possible. But if coffee cup is losing its heat to the surroundings, then it is possible. So then entropy of the system 10 divided by 45 plus 273 and the surrounding temperature also 10 divided by 25 plus 273. Finally the equation will become as plus 0.00211 joule per Kelvin. So that the minus value will not happen. Practically it is not possible. This positive value will be possible. Okay, so from the coffee cup, heat is transferred from the coffee cup to the atmosphere. It is not at all gaining the heat from the atmosphere. But you can have a doubt. In a zeroth law of thermodynamics, I told that 10 degrees Celsius coffee cup will be absorbing the heat and attaining the room temperature. It is possible. Whatever the materials, whatever the liquid we are keeping in a room temperature, that room temperature, that liquid, that materials will be attaining the room temperature. Above the room temperature is not at all possible without giving any external heat input. That we should know. We shouldn't get confused about that zeroth law of thermodynamics to applications of this third law of thermodynamics. So if we keep a 10 degree Celsius of a coffee cup, that will be attaining the room temperature. That will be gaining the temperature from 10 degrees Celsius to 25 or 28 degrees Celsius. That will not exceed to room temperature. That is not at all possible. That coffee will not exceed the room temperature. If you give the external heat supply heat input to that coffee cup, then it will be above the room temperature. So that we should know the difference between those things. Right. So we all know that the entropy of the universe will be increased. So second law of thermodynamics will be giving the direction of heat supply. So how the heat is transferred from one region to another region, what is the direction takes place. Second law of thermodynamics will be stating this. Then the internal energy. So this also one of the important property for solving the equations in a thermodynamics. So internal energy, the energy which is already available in the system. That is internal energy. Mathematically, it will be denoting as a MCP or MCV delta T. Sorry, MCV delta T. If the change in internal energy will be denoted as a del E or del U, U2 minus U1 or E2 minus E1. Right. Then enthalpy. Enthalpy also one of the important property. H equal to U plus PV. Internal energy and the work what is happened by using that internal energy, that is known as a enthalpy. Available energy which can be converted into a useful work, that is enthalpy. Entropy is a unavailable energy which cannot converted into a useful energy, that is known as a entropy. Enthalpy is just opposite to the entropy, that the energy available in the system, it can be converted into a useful work. The mathematical relation for the enthalpy is H equal to U plus PV. Next, the laws of heat transfer that we should know. So this is the one of the thermodynamic is a basic of for this three laws. So without thermodynamics, we cannot come to know about these three laws. Fourier's law. So Fourier's law will be speaking about the heat conductions. So thermodynamics, temperature is a transfer from heat is transferred from one point to another point. That is the thermodynamics. So we should know what is Fourier's law of heat conduction in a solid materials, how the heat is transferred. That is Fourier's law. It is also one of the application from the thermodynamic systems. But we will be studying these concepts in the heat and mass transfer subject. But this is also full 100% related with the thermodynamics concept. So that's why I have taken this slide. This is only one slide about the heat transfer concept. From this Fourier's law, we came to know about the heat conduction between the two solid materials. So the mathematical formula for this Fourier's law of heat conduction is that Q equal to HA dt divided by dx. So dx is a thickness. Dx is the thickness of the materials. So since we are if we are about to study the thermodynamics, we should know the thermal conductivity and the thickness of the materials, because heat transfer rate will be depending upon these two only: thermal conductivity of that particular material and also thickness of the materials. If the thickness is increased, the heat transfer rate will be reduced. If a materials will be having a low thermal conductivity, we cannot achieve what heat transfer rate we should need. So before to know about the heat transfers from one point to another point, we should know what is the materials we are using and what is the thickness of that particular material, and how the what thermal conductivity value of that particular material. Thermal conductivity of the material is that the amount of heat conducting ability. So generally copper will be having a maximum thermal conductivity. How much amount of heat will be conducted by that particular materials, that will be denoted as a thermal conductivity. So Fourier's law will be speaking about the heat conduction rate, heat conduction in a two materials. Newton's law. Newton's law will be speaking about the convection. So heat is a transfer from the solid materials to fluid medium, maybe liquid or air. Fluid may be liquid or air. So how the heat is transferred from that solid materials to fluid medium. So parallel flow counter for heat exchanger we might have studied in this application. So Newton's law of cooling. The formula for this mathematical relation for this Newton's law of cooling is that HA delta T. H is heat transfer coefficient. So many of the students doesn't know about the definition for heat transfer coefficient. So heat transfer coefficient is nothing but force of heat travel. So heat is traveling from one point to another point. In how much speed the heat is traveled, that is known as the heat transfer coefficient. In how much speed heat is traveled from one point to another point, that is heat transfer coefficient. Next one is Stephen Boltzmann law. So it will be speaking about the radiation process. Stephen Boltzmann constant sigma will be there, 5.67 into 10 to the power minus 8 watt per meter square Kelvin power 4. So heat transfer rate is directly proportional to the fourth power of its absolute temperature. So this also will be speaking about the heat transfer rate. Heat transfer rate in a radiation process. Insulations. So insulation in the sense, if we want to study about the heat transfer rate or any heat conducting capacity of the materials, we should know we should create insulation. If any system is perfectly insulated, that system will not be losing its heat to the atmosphere easily. So there are many insulation materials are there, like asbestos, glass wool, wood materials will be there, that will be retaining the heat for particular time. So insulating the thermal components is very much essential to maintain the heat, to retain the heat. Many of the faculties or students doing project. Faculties are doing project for their PhD students are doing project for their final year work, final year projects. So for any thermal concepts, for any thermal systems they are manufacturing, they are doing experimental work, they are going for experimentations, that system should be perfectly insulated, because they will be studying about full and full heat transfer. So for that we have to insulate that system in a perfect manner to retain the heat. Okay, so the heat loss to the atmosphere will be minimized. That is called insulations. Then thermal conductivity, unit of thermal conductivity, watt per meter Kelvin. Heat transfer coefficient, I told you na, heat transfer coefficient, watt per meter square. This is watt per meter Kelvin. Thickness also I have told. So if the thickness of the material is very less, heat conducting rate will be maximized. The thickness of the material is high, so we can we cannot achieve the heat what we expected. Thank you.
Thank you, Divakar.
Thank you.
Is there any queries?
Any
You can,
any questions, any doubts are about different types of thermodynamics law, entropy concepts, the properties? Anybody having any doubts? Already, since we are faculty members, we know this concepts already very well. So just we can make it this session as an interactive sessions to know about this concept. So any doubt, any clarifications from your side?
so I think no. So
Faculties, you can interact freely. Thank you very much, Dr. Divakar, for your wonderful presentation.
Thank you, sir. Thank you. Thank you, sir. Thank you for the opportunity, sir.
Yeah, thank you. Where are you put up now?
Sir, you were asking where I am working.
No. Now where are you staying?
Sir, I am staying in my native, sir, Karur.
Karur, huh?
Karur, sir.
Through online only teaching and everything in that.
Yes, sir. Yes, sir. Yes, sir. In Andhra only, online only we are teaching, sir. They are asking us to come to college, sir. Actually, they are keeping college morning 8 o'clock to 11 o'clock.
Okay.
For 3 hours, they are asking us to come. But in Tamil Nadu, there is a lockdown, sir. So, அதனால போக முடியல சார் அங்க.
ஓ, இப்போ யார் பிரின்சிபால்?
சார் அங்க இப்போ வந்து சுப்பாராவ்னு ஒருத்தர் இருக்காரு சார். சுப்பாராவ். ஆல்ரெடி அவர் சார்
குவிஸ் ஐடி இருக்கு ஒண்ணா?
ஆமாங்க சார். குவிஸ் ஐடில தான் அவர் முன்னாடி பிரின்சிபலா இருந்தாருங்க சார். இந்த குவிஸ் டெக்ல இருந்த பிரின்சிபல் வந்து இப்போ ரீசெண்டா 2 மாசத்துக்கு முன்னாடி ரிசைன் பண்ணிட்டாருங்க சார்.
ஓ சரி.
அதுக்கப்புறம் இவரு குவிஸ் ஐடில இருந்தவர் இங்க வந்துட்டாரு சார்.
ஓ சரி சரி சரி. ஓகே.
குவிஸ் ஐடில கம்ப்யூட்டர் சயின்ஸ் ஹெச்ஓடியா இருந்தவரை இப்போ அங்க பிரின்சிபலா போட்டாங்க சார் குவிஸ் ஐடில.
ஓ சரி சரி சரி.
ஆமாங்க சார். குவிஸ் ஐடி க்ளோஸ் பண்ணிட்டாங்க சார். அட்மிஷனே இல்ல சார் சுத்தமா. இப்போ அந்த ஃபர்ஸ்ட் இயர்க்கு அட்மிஷனே வரல.
ஓ சரி.
அதனால அதை க்ளோஸ் பண்ணிட்டாங்க சார். அதனால அங்க இருக்கிற ஃபேக்கல்டி கொஞ்சம் கேலிபரா இருக்கிற ஃபேக்கல்டி எல்லாம் தூக்கி இந்த இன்ஜினியரிங் காலேஜ் இதுக்கு போட்டாங்க சார்.
ஓ சரி சரி. ஒர்க்கிங் என்விரான்மெண்ட் நல்லா இருக்காங்க
சார்? பரவாயில்ல சார். இங்க ஒன்றும் பிரச்சனை இல்லை சார். இங்க கொஞ்சம் நம்ம தமிழ்நாடு ஃபேக்கல்டிக்கு கொஞ்சம் இம்பார்ட்டன்ஸ் கொடுக்குறாங்க சார்.
ஓ சரி சரி.
எல்லா டிபார்ட்மெண்ட்லயும் ஒரு 3ல இருந்து 4 ஃபேக்கல்டி தமிழ் ஃபேக்கல்டி இருக்காங்க சார்.
ஓ சரி.
நம்ம இங்க தமிழ்நாட்டுல இருக்கிற காலேஜஸ் அளவுக்குலாம் ரொம்ப ஸ்ட்ரிக்ட் ரூல்ஸ் அந்த மாதிரி எல்லாம் எதுவும் ஃபாலோ பண்றது இல்லை சார்.
ஓ சரி.
இதெல்லாம் டாக்குமெண்ட் எல்லாம் மேக்ஸிமம் ஃபேக்கா தான் ரெடி பண்றாங்க. அப்படியே எல்லா அப்ளிகேஷனும் வாங்கிடுறாங்க சார். அப்படியே ஏதோ ஓரளவுக்கு அப்படியே ரெடி பண்ணி எல்லா அப்ளிகேஷனும் வாங்கிடுறாங்க சார். எம்பிஏ ஈஸியா வாங்கிடுறாங்க, நேக் வாங்கிடுறாங்க. ஆனா பெருசா டாக்குமெண்ட் வந்து கரெக்டா இது பண்ற மாதிரி தெரியலங்க சார்.
ஜாயின் பண்ணி இப்போ எவ்வளோ நாள் ஆகும்
சார்? இப்போ 6 months ஆச்சு சார். இப்போ ஜான்ல தான் ஜாயின் பண்ணேன் சார்.
ஓ சரி சரி. சேலரி ஃபுல் கொடுத்துறாங்க?
சேலரி எல்லாம் கொடுத்துருக்காங்க சார், ஒன்றும் பிரச்சனை இல்லைங்க சார்.
ஓகே ஓகே.
இப்போதான் வைவா முடிச்சேன் சார். இப்போ 2 weeks முன்னாடி தான் வைவா முடிச்சதுங்க சார்.
ஓ ஓகே ஓகே. வெரி குட் வெரி குட்.
அதான் டிசி சப்மிட் பண்ணிட்டு அப்படியே அங்கே போய் ஜாயின் பண்ணிட்டேங்க சார்.
ஓகே ஓகே.
ஓகேங்க சார்.
தேங்க்யூ தேங்க்யூ.
தேங்க்ஸ். தேங்க்யூ சார்.
Okay, thank you, Divakar.
Thank you, sir. Thank you. Thank you, Mr. Pradeep sir, for this wonderful opportunity.
Thank you, sir.
Thanks, sir. Thank you for all.
Sir, session
Thank you,
closed
thank you,
from-
sir. Thank you.
Thank you, sir.
Okay, sir. Thank you.
Thank you.